Alright, hello everyone and welcome to a new practice lesson from the time complexity chapter. So again, we have a function which is named print pairs and has only one argument, right? So yeah, similar to the other function in the practice number 1, this function is going to print us some pairs, but it's going to do it in a different way, obviously, right? So I takes each and every value from 0 to n minus 1, so this is actually the same as before. But now j starts with the value 1, and as long as j is less than or equal to n, we print the pair I and j, and then we multiply j by 2, right? So let's take an example to see how these pairs actually look like, right? So I'm going to take, for example, n equals 8, right? Let's see what are the pairs here for n equals 8. As you can see, the first value of I is 0, obviously, right? So I equals 0 on the first iteration of this for loop, and j starts with 1. Okay, so let's write here actually j equals 1. Okay, and yeah, what's going to happen? We enter the while loop and we print the pair ij. So the first pair that we are ever going to print is 0, 1. Awesome. Then we multiply j by 2. So now j becomes 2. Perfect. Enter again the while loop because 2 is less than or equal than 8. Print this pair. So the next pair that we are going to print is 0, 2. J gets again multiplied by 2, right? J equals 4. It's still good. We are going to print 0, 4. J multiplied again by 2, so J becomes 8, right? And we print the pair 0, 8. And now this is the final moment as j becomes now 16, which is not anymore less than or equal to 8, right? So yeah, for I equals 0, we had 4 different values of j and ultimately 4 pairs that we have printed. Cool. Now, what's the next step? Of course, we increase I, right? So we have to see what happens when I equals 1. Well, I equals 1, j equals 1, right? Cool. And what's going to happen? We enter the while loop, and the first thing we do, we print the pair. So the first pair that we are going to print for I equals 1 is 1, 1. Okay, then j gets doubled, so j is equal to. So we enter again with j equals 2, we print again the pair. The pair is going to be 1, 2. J gets doubled, becomes 4, still less than or equal to 8, so we print the new pair, which is 1, 4. Gets doubled again, so its value is now 8. And yeah, we can enter again the while loop, print the pair, j gets doubled again, so this time it's going to be 16, and yeah, this is the first bad value as it is greater than 8, right? So there is one interesting thing here that we can notice. I mean, yeah, we can go on and try each and every of the rest 5 values for I, right? 2, 3, 4, 5, 6, 7. But that's not the point here. We are going to waste a lot of time when we can really make an observation right away on the spot. That observation is that no matter what was the value of I, right, 0 or 1, j actually acted the same, right? So started with 1, was always doubled, right, until it hit a value greater than n. And as you can see, for each of these pairs, right, the value of j is actually equal to the one with I equals 0, right? So yeah, I now from 0 became 1, but as you can see, j stays the same, 1, 1, 2, 2, 4, 4, 8, 8. This is very interesting, and is the first observation that we can actually do. Because unlike the previous problem, right, the previous algorithm, where if you remember, j started with the value I plus 1, right? And yeah, so there j started from I plus 1 and basically was incremented until it hit the value n minus 1, right? Now this j starts with 1, always gets doubled, and should be less than or equal to n. So there is no I involved, right? So the first observation is that j is going to, again, act the same no matter the value of I. So the number of iterations this while loop is going to perform will be the same no matter the value of I, right? Here, if you remember, the number of iterations depended on I. It was n minus 1 minus I believe, or something like that, right? So I was an important factor. But here, I doesn't matter. So what we can do is, first of all, because we have two nested loops, right? The first one is for I, and the second loop is this while, which is for j. First thing we can do, because again, it's super simple, j doesn't depend on I, is actually compute how many iterations does the while loop do. And then of course, each of these iterations is going to be performed for each of these iterations in the outer loop, right? So let's start with how many iterations the while loop does. Well, we can take a look at the example, right? And see what are the values that j take. Well, 1, 2, 4, 8. Okay, this is interesting. This is very similar to what we have done in the previous lesson, right? As you can see, j starts from 1 and is always doubled, right? So j will actually be always a power of 2, right? So no matter the value of I, right? I can be anything. I equals, I don't care, something. No matter its value, j always starts from 1, which is 2 to the power of 0, and gets multiplied, right? By 2. 2 to the power of 1, 2 to the power of 2, and so on and so forth, until, of course, it hits some point, 2 to the power of k, which is still correct, right? And then it becomes 2 to the power of k plus 1, gets doubled one more time, but this value is the bad one, right? Just like we did here, right? And here, but I forgot to write the 16. 8 was good, but now the 16 is not good because it's greater than 8, right? So yeah, basically those are the values that j take. For each of these values, of course, there corresponds one iteration in the while loop. So how many values does j take? Well, the real question is, what is the value of k, right? Because as you can see, for each value, we have a different exponent, right? The exponent starts from 0 and gets incremented at each step. So the question is, what is the value of this k? Well, we know that, right? We have just found out what is the value of the k. Who is k? Again, k is the greatest integer such that 2 to the power of k is less than or equal than n, right? That's our constraint. J less than or equal than n, right? 2 to the power of k plus 1 was greater than n. That's why it was bad. So k, it's pretty obvious. It is log of n, right? Of this value that we care about. So actually, we have each and every power of 2, right? Starting from 2 to the power of 0 to the power of 1, all the way to 2 to the power of log n. So we have a total of log n plus 1, right? Think about it. From 0, 1, 2, all the way to this k, which is log of n. How many different values? How many different exponents? Log n plus 1, right? So for each value of I, no matter what is the value of I, we don't care about that. We have log n plus 1 iterations or different values of j, right? So let me just clear a little bit here to make some room and write here log n plus 1. Awesome. Now, of course, I forgot to say it, but it's pretty obvious. This is constant. The printing is again constant. The initialization is, of course, constant. So if we think about what is the time complexity of this piece of code, we are going to see that we have constant operation, a while loop, which performs a total of log n plus 1 iterations, and inside only constant operations, right? So not taking into account any constant, we can say that the final time complexity only of this piece of code is log n, big O of log n, right? So why do I care about this piece of code? Because this is what is getting executed each time we enter a new iteration of this for loop, right? So for each of these, how many iterations are here? Well, we know how to compute how many values are in a range now, right? And it's pretty obvious. If let's say, I don't know, I had the range 0, 11. Let's take an example, right? How many integers are between 0 and 11? It's 12, right? You can count them. It's super obvious. So yeah, in this range from 0 to n minus 1, I have exactly n integers. And of course, I is going to take the value of each and every one of them. And for that value, I'm going to execute again this piece of code, right? So I have here, let me clear this so I make some room. This for loop performs a total of n iterations, right? So for each of these n iterations, I do a big O of log n. So what's the final time complexity? Am I going to add them together? Of course not. I'm going to multiply them together, right? So the final time complexity of this algorithm is big O of n log n, right? So be very careful when you have nested loops. You always multiply the number of operations with the number of iterations that each of them does, right? So yeah, that's it, guys. The answer is big O of n log n. Make sure you understand this, and I'll see you on the next one. Bye.